This is Torrance student with Lab 7, Part 1 at home, where we are going to try and find the mass of our black hole. First, our main problem and some of our objectives were that we have a star orbiting around a black hole of unknown mass. So using the code that we developed last week in lab, which shows the relationship of gravity between objects and given data, we are then going to predict the mass of the black hole in kilograms. We're also going to discuss the relationship between FNet and our change in momentum. Our main result of this lab was to find the mass of our black hole, which I found mine to be 3.56 times 10 to the 31st. And we also wanted to prove that FNet and our change in momentum are going to be equivalent for all the components. So some of the things going to be discussed in this lab, that our FNet and then our FNet parallel and our FNet perpendicular values are all going to be equal, and I'm going to show those by the codes that we are running. So on this first code here, I was working to find the mass of my black hole. So I had this code took in the position of my star and black hole, and we're going to run it and see what our mass is giving us. So it runs very quickly. And here in the end, you can see that it outputs that there's my mass is 3.56 times 10 to the 31st. This code pretty much just used the gravitational force equation, which is G times M1 times M2 over R squared. It's giving me my output, which is my mass of the black hole, and it just solved it for my M1. So once we've proven that, I went over to another computer, and here, over here we're just going to kind of explain what does all this mean. Here we're taking the code that we created last week in lab, which is going to output us our three arrows. Here we uncommented these, and down here it does print this mass of our star and how many Earth years it would take. But when we run this, we're just kind of looking and observing the three different arrows that it outputs. Our first one, which is our black arrow, is the FNet arrow, and it's always going to be pointing towards the center because of this centripetal force. Our blue arrow, which is the FNet parallel, is parallel to momentum, so that's going to be our tangent line, as you can see it down here. Our red arrow is the FNet perpendicular, and it's perpendicular to momentum, which means it's going to be inward. So we know that our FNet parallel plus our FNet perpendicular is just equal to our FNet. So this is kind of how we get the sizes. Based on the sizes, that's how we know where our FNet arrow is. These just represent the magnitude of the force. So our three arrows, we're kind of just trying to prove that they're equal, because we know that FNet equals dP over dt, and then our FNet parallel equals dP over dt parallel, and FNet perpendicular equals dP over dt perpendicular. So if we were going to run these all over again, we would just get that our values are equal. So we want to discuss kind of how the FNet was different from our change in momentum. Our FNet is not really observable, but our dP over dt is. They aren't the same thing, but they do have equivalent values. So we know that our FNet parallel is going to be our that changes the magnitude of momentum, and while our FNet perpendicular changes the direction of our momentum. So when we ask the question, like, what if we wanted to find like a different mass, we're still going to use our gravitational force, which is determined by mass. So we use the same equation that we used in the very first module I ran, which is F-grav is equal to gravity times m1 times m2 divided by our radius squared. You're going to be able to tell if the mass has changed because it would change the star's pattern, but only the force. So what if you had a smaller circle or a larger circle? A smaller circle would mean that there would be a weaker gravitational force, which means that you'd have a smaller mass. If you had a larger circle, you would have a stronger gravitational force and a smaller mass. If you were to happen to have the same mass, you would just pretty much have the same circle, which is equal to our force of gravitational. So overall, our main object was to find the mass of our initial black hole and explain the FNet, parallel, perpendicular, and FNet, and that's what we did.